It is a great pleasure to introduce Ilijas Farah from York University, who will be our colloquium speaker today. Ilijas did his bachelor and master's at University of Belgrade, and then a PhD at University of Toronto, for which he received the Sachs Prize for the best PhD thesis in mathematical logic worldwide. Ilijas is a world leader in two different branches of mathematics, in mathematical logic and operator algebras. He was an ICM speaker in Seoul in 2014. One of his biggest achievements is a resolution of a problem regarding automorphisms of the Kalkin algebra, which might be related to his talk today as well. Besides the scientific accomplishments on his account, Ilijas also has many PhD students who are now very successful, are receiving ERC grants and also Sachs prizes. So I think he's a prolific in all different aspects. Let's listen to his talk.
Thank you, and thank you for the invitation. It is a great pleasure to be here. And as Martin said, so I'll be talking about logic and operator algebras, although I've spent last almost 20 years now trying to convince people that they are not that different areas as most people might think. This talk is roughly based on a very long survey paper with the same title, which has nothing to do with pandemic. We actually didn't even notice. I was sending paper to people, and they would say, "Oh, a nice title." And so, yeah, what do you mean? You know, when you're thinking about something, you just don't realize that word may mean something else as well. So anyways, this is going to be just a small part of the subject, and it is something that I've been thinking about basically ever since I got my PhD. Oh, maybe. No. Huh. Okay, I was warned this may happen. Yeah. Okay, so I think I just pressed some. No, okay, good. Thank you. Thank you. Yes. Okay, so tech support is fantastic here. It's great to see. So this is we have this little family tradition of going to wildlife photographer of the year. I don't know if you can see it, but actually this is actual photo. This is not photoshopped, of baboon, I think, riding a deer for whatever reason. Which has nothing to do with my talk, but I just thought it's good to break the ice somehow. All right, what does have to do with my talk is Hilbert space, and of course 1/2 plus 1/2 is equal to 1. What do I mean by that? Well, I guess Hilbert space is one of the most important objects in mathematics, so it probably doesn't require reminding you, but I'll remind you anyway. We can think of little L2 of n, right? So just a space of all square summable sequences with a square root norm and inner product. And what is important about Hilbert space is that it is its own dual. That every functional is implemented by conjugate linear by a vector in the space. And so every Hilbert space has orthonormal basis, and basically every three-dimensional subspace looks exactly like what we at least think we see all the time. Question is, are we right? Is the space really Euclidean space? But that's a different thing. Basically, Hilbert space by itself is actually quite boring because no matter what you come up with, you end up with the same thing. So here you have the big L2 space, which is isomorphic and isometric with a Hilbert space. So really interesting things start happening when you start talking about operators, bounded linear operators of Hilbert space. Before I go on to that, Hilbert spaces are complex Hilbert spaces. So I want my polynomials to have roots, and I want my spectral theorem. We'll come to that. So B of H is the algebra of all bounded linear operators. We can add operators, we can compose them, which is multiplication, and also importantly, there is the adjoint operation, which exactly corresponds to this Hilbert space being dual, right? In general, if you have linear operator between two binary spaces, then the adjoint goes between their duals in opposite direction, but here it's all in the same place. And that adds a lot to the structure. Special case is when your space is finite dimensional, then of course this is just n by n matrices, n is the dimension. And as we know, you always have a change of basis for a linear transformation, which really translates into saying that if you look at n by n matrices, every automorphism of that algebra is inner. It is implemented by unitary. Well, exactly the same thing applies even if you're in infinite dimensional Hilbert space, and proof is actually similar, basically. Just pick a basis and just see where the basis vectors go, and there you have your operator. Now, a good way to think about, I mean, as many useful pictures, it is not completely correct, but it is quite useful to think about operators on Hilbert space as big matrices. Just fixed basis, and you just have a big matrix whose entries are just inner products of image of vector EI with vector EJ. Right, so every automorphism is inner, and it is implemented by unitary. We'll be seeing conjugation by unitaries quite a bit later on in this talk. But first, modular compact perturbations. Now, I'm going to fix throughout, maybe I should say that. So whenever I say H, I just mean L2 of n, separable infinite dimensional Hilbert space n, Hilbert space H. And in the algebra B of H, there is a unique ideal, which is non-closed, is the ideal of compact operators. Right. So another good thing about Hilbert spaces is that operator is compact if and only if it is on closure of finite rank operators, if and only if the image of the unit ball is compact in the norm topology. In binary space, it's slightly trickier, but here everything works in the most trivial possible way. And the story here begins 100 years ago. First paper by Hermann Weil. He was studying compact perturbations of pseudo-differential operators, I think. And so what that means, we have your operator, and you just perturb it so that the difference is a compact operator. Now, we all know that self-adjoint matrices can be diagonalized in finite dimensions. And most of us know that if you have a self-adjoint operator in Hilbert space, it in general cannot be diagonalized. It doesn't have to have a single eigenvalue. But what Weil noticed is that you can find a compact perturbation, which is still self-adjoint and diagonalized. That's, I guess, exercised by today's standards. And then von Neumann noticed that if you have that, then you have this theorem here, that if you have any two self-adjoint operators on infinite dimensional Hilbert space, then question whether one is unitarily equivalent to a compact perturbation of the other, that's equivalence relation, can be decided by a very simple invariant, which is the essential spectrum of that operator. So you just take the spectrum, remove all isolated points of finite multiplicity, and that is a simple invariant. Now, this is remarkable in sense of the fact that if you actually want unitary equivalence on the nose, the invariant is much more complicated. It involves spectral measure, and there is more logic than I want to go into. But so for self-adjoint operators and equivalence modular compact operators, the picture is quite simple. And a couple of decades later, by Berg and Sikonia, this was extended to normal operators. That normal just means operator which commutes with its adjoint. And again, those operators can be diagonalized modulo compact perturbation. Now, if you want to go beyond normal, well, to the best of my knowledge, we don't understand non-necessarily normal operators to the extent that the invariant subspace problem is still open. Actually, Per Anflo posted a solution last year. I hope it's not going to take 10 years this time again before somebody understands what is going on, right? Famously, he solved other problems. It took a while for people to catch up. But anyway, point here is that basically going beyond normal operators gets really tricky. So instead, we look at C-star algebras. So these are subalgebras of this algebra B of H. So B of H is Banach algebra, is addition, multiplication, and the adjoint. And if you have a subalgebra which is also self-adjoint and closed in norm, that's called C-star algebra, and everything isomorphic to something of that sort is called a C-star algebra. Now, what are examples? Well, n by n matrices and B of H itself, right? So if they are the biggest one, but also somewhat less obviously, if you take a complex Hausdorff space and look at all complex valued continuous functions, this has a structure of C-star algebra. It is an exercise to see why this can be represented on a Hilbert space. I'll leave it to you. But more importantly, for what I'll be talking, these are all unital abelian C-star algebras. There is a beautiful theorem, an old one by Gelfand and Naimark, which says that if you have an abelian C-star algebra, then somehow out of that algebra from its spectrum, you can dig out this compact Hausdorff space. Algebra is isomorphic to something of the form C of X. And not just that, actually, there is equivalence of categories, which is contravariant. So isomorphisms between, actually morphisms between abelian C-star algebras actually correspond to continuous functions between compact Hausdorff spaces. And now inside any C-star algebra, one can define spectrum. I'm talking about unital. Actually, most algebras are going to be unital. At least talk up to some point. Then we'll. But if algebra has a unital, spectrum is just defined, just like in algebra. And remarkable consequence of Gelfand-Naimark theorem is that we have continuous functional calculus. So if you take a normal element in any C-star algebra and generate subalgebra by that element and the unit, what you get is exactly continuous functions on its spectrum. And that element goes to identity function, polynomials go to obvious place where they're supposed to go to. So this is a very useful way of thinking about these things. And now, one special case, if you have a normal operator on Hilbert space, just see what is its spectrum. It is going to be compact, non-empty subset of the complex plane. And C-star algebra generated by it is exactly continuous functions on that. So, we saw in Berg-Sikoniya theorem that it is about normal operators. So this really, you can think about it as abelian C-star algebras. And indeed, that's what I will be doing. But now, the modern sort of big picture idea is, where von Neumann just looked at perturbations, well, why not just mod out this idea of compact operators and see what happens? So K of H is the idea of compact operators, and the quotient algebra is the Kalkin algebra. By pi, I'll be denoted quotient map. Now, one not obvious thing at all is that Kalkin algebra is a C-star algebra. It is isomorphic to algebra of operators. So some Hilbert space necessarily non-separable, quite big actually. But it is C-star algebra, and we have continuous functional calculus. It has this nice behavior. And essential spectrum of some element is exactly spectrum in the Calkin algebra of its image. And with that observation, we can restate Weyl von Neumann-Berg-Zikonia theorem as saying that, let me actually draw it. You see here we have this, this normal operator A. Then C-star algebra of A is really just isomorphic to continuous functions on the essential spectrum, actually on the spectrum of A. And we just think of it as being embedded into the Calkin algebra. And what the theorem says is that if these essential spectra are the same, then the operator is unitarily equivalent. Namely, if you have normal operator, and if this is injective map, then all of these star homomorphisms are unitarily equivalent. Right? So now there is important point that I am starting from a normal operator in B of H, which is not the same as picking a normal operator here. This way, statement about operators translates into statement about singly generated abelian C-star algebras. And that's where Brown, Douglas, and Fillmore come. So what they did is the following. Well, never mind abelian, never mind operators. Let's just look at it abstractly. Take separable unital C-star algebra and look at all possible star homomorphisms from that algebra into Calkin algebra, which are injective and unital. And mod them out, so there is this mod out by unitary equivalence. Right, so we have some quotient structure there. But there is more than just quotient structure. There is algebraic structure. You see, this Hilbert space, if you take direct sum of two copies, you just get the same thing. And if you look at bounded linear operators on that, that really corresponds to 2 by 2 matrices over bounded linear operators over original space, right? Because you know, we have H plus H. Just takes a little moment to convince yourself in that, and then also when you model the complex, still holds. So Calkin algebra is invariant under tensoring with 2 by 2 matrices. And what that means that we can define, for example, addition in X of A as follows. Now, these square brackets just mean that I'm looking at unitary equivalence class. And what you have on the right-hand side, sorry, this matrix, well, whether it's phi00 psi or psi00 phi, it doesn't matter. They're unitarily equivalent. You can flip the elements of the argument by just conjugating with appropriate unitary matrix. So what we have is semigroup. Right? So this X for any separable unital C-star algebra is going to be semigroup. Now, I haven't used separability here. This makes sense even if algebra is non-separable, but one doesn't get interesting results. So we just stick to separable. Okay, so we have a semigroup. And what Brown, Douglas, and Fillmore proved in the 70s is that if your algebra is separable and abelian, then it's actually a group. And one of the key parts of this is the so-called Voiculescu's theorem, which says that if you have this injection for any separable C-star algebra, if that injection lifts by a star homomorphism to B of H, then any two such trivial extensions are unitarily equivalent. And that is the unit. So unit in this semigroup is provided by the trivial extension, but by the one that leads to a homomorphism. Right. So they prove much more than this. This actually calls for nuclear C-star algebras, and we'll come back to that. But just to get some examples, if space X is contractible, then this semigroup, this group is trivial. But for example, if you take a real projective plane, you actually get torsion. group is Z mod 2Z. It is kind of weird. But what I want to talk about is this question here. Can automorphism of Kalkin algebra act on any of these semigroups non-trivial? You see, automorphism group, of course, acts on all of these. Can actually be non-trivial. Well, for that, let's look at unit circle. So what is X of continuous functions on the unit circle? Exactly. Right, because if you have this algebra, it is generated by a single unitary, because you have normal element whose spectrum is inside the circle, it's a unitary operator. And of course, for unitary operators, all that matters, once you know the spectrum, is what is the Fredholm index. So this is just Z here in Canada. Right. Now, of course, the one that corresponds to 0 is the one that lifts, that's the unit. But now, how can possibly automorphism group act on this? Well, Fredholm index tells you exactly what roots your unitary has. And automorphism cannot send something with square root to something that doesn't have square root. So all that you can do is act trivially or flip plus and minus. And that is really the question. So Brown, Douglas, and Filmer figured out a lot about how this works, but here is the simplest question they couldn't solve. Namely, does Kalkin algebra have an index reversing automorphism? So this Z here is really, it's really K1 group of the Kalkin algebra. And acting on X of the circle would exactly be just the same as flipping K1 by an automorphism. So can you have automorphism like that? Now, it is an exercise to see that if you have inner automorphism, then you have to preserve the Fredholm index. So the test question for that was, does Kalkin algebra can have an outer automorphism as well? And this was answered by Phillips and Weaver, who proved that under continuum hypothesis, Kalkin algebra has as many non-trivial outer automorphisms as possible. None of those automorphisms flip the index. That they are basically constructed by putting together inner automorphisms in a non-trivial way. And it's something that logicians know that continuum hypothesis is good for doing. Okay, so if there are any questions, just let me know. But we go on. So here's a famous citation by Bertaglia. Right, so let's look at the commutative version of that question. Now, what is commutative version? So remember, I said you can think of operators in B of H as big matrices. Well, let's look at diagonal matrices. Right, so those are operators which are diagonalized by a fixed orthonormal basis. And what that gives you is just copy of L infinity, just bounded sequences of complex numbers. So this is abelian subalgebra of B of H. And compact operators among those are exactly the sequences that converge to 0. So this quotient space, L infinity mod C0, is a commutative version of the Kalkin algebra. Well, it turns out it has been studied before. Walter Rudin proved that continuum hypothesis implies that this algebra has two to the continuum many automorphisms. Note, every non-trivial automorphism of abelian algebra has to be cannot be inner. You don't have inner automorphisms. So we want just to decide what means non-trivial. But Shah proved in 1979, which is a few years after Brown, Douglas, Fillmore. Basically, he gave what is the right definition. So there is some forcing extension in which every automorphism L infinity mod C0 is implemented by unitary in the Kalkin algebra. Right? And these are the actually unitary in the normalizer necessarily. You want something normalizer, which is exactly the right definition of trivial. And we'll be seeing this later on, that always there is this question of this quotient structure. So what automorphisms does it have? What are the ones that I can construct? And once you figure out what you can find, the idea is to prove that there is nothing else, that you didn't miss anything. So okay, so that's this. Now you see, when I stated these theorems, this is not how they stated it. We have two dualities at work here. The one that they stated all of these results in terms of Boolean algebra, power set of natural numbers modulo Fréchet ideal of finite sets. Now, Boolean algebras are in duality with Stone spaces, but also C-star algebras are in duality with compact Hausdorff spaces. That's what abelian unital C-star algebras. That's what I mentioned before. So basically, what Rudin and Sherlock were working with was not C-star algebras, but Boolean algebras of their projections. But that doesn't really matter for us. What really matters is that we have this bigger picture here. Sherlock's proof was ingenious ad hoc construction of forcing extension of the universe, which just model tailor-made for that purpose. And one could object that continuum hypothesis is this nice natural axiom, and somehow it should have more weight than some obscure model. But one of the main points of my talk is that that's not how we should think about it. That there is a very coherent theory which is sort of alternative to continuum hypothesis, by so-called forcing axioms. So let me briefly just say what it is. So assume you have some class of compact Hausdorff spaces. I mean, you can as well assume that your class just contains something like interval 0, 1. This will do for a moment. And now, of course, we have the category theorem. Intersection of countably many dense open sets is still dense. We'll just push it to the next cardinal. F1 is the smallest uncountable cardinal. And just postulate that in any compact Hausdorff space in your family, if you have F1 many dense open sets, the intersection is non-empty. Now, even if you look at this one, for any point, the complement is dense open, and intersection being non-empty just means that there are more than F1 many points here. So continuum hypothesis fails. But that's the easiest application, and actually forcing axioms go a long way. For certain spaces, this is just outright false. It's not too difficult to construct compact Hausdorff space in which there are F1 many dense open sets with empty intersection. But there is amazing theorem by Foreman, Magido, and Shaw that there is the largest family of compact Hausdorff spaces for which you can have this axiom. Family is defined in a very mathematical way, so I'm not going to attempt. But this axiom is consistent with ZFC, assuming certain large cardinal axioms. Now, I said all sorts of things that I don't want to go into. You can ignore large cardinal axioms for the purpose of this talk. Actually, none of what I'm going to say has to do with this. Let me just say that basically large cardinals are, yeah, no, I shouldn't say anything. So I'll just go ahead. And this axiom is called Martin's maximum. And what matters for us is that Sherlock and Statrans proved that Sherlock's result actually holds, assuming fairly mild forcing axioms. So basically, this gives a coherent analog to continuum hypothesis, which gives rigidity. So it gives us, at least for L infinity mod C0, that all automorphisms are trivial. And as Martin mentioned, thanks for the spoiler, so I did manage to prove that forcing axioms imply that all automorphisms of the Calkin algebra are inner. And that implies that if you assume forcing axioms, then there is no K-theory reversing automorphism, and automorphism group acts only trivially on X of any C-star algebra, separable or not. This gives extreme rigidity. Now, this is just one result in entire cycle family of results along the similar lines. So, like they this was it depends. So I'm here putting 2011 because that's when paper appeared, but it was actually 1 year after. So I proved it. Essentially, I learned about this, and because I was doing some other work on similar things, just I said, okay, so just tell me definition, I can prove it. So it was, I proved so many things along these lines that it didn't take long. So from Rudin to Scheller, it took a quarter of a century. And actually, interesting thing is, Rudin was in 56, and Philip's view was exactly half century later. And Scheller was 79. This took less than half century. So yes, but anyways, so this is not an isolated result. There are many similar results. I'm just stating the most recent one with Alessandro Vignati, one of my students that Martin mentioned, and Ben de Bont, also student right now, that you have analogous rigidity results in other categories. Now, in each category, one has to figure out what is a trivial automorphism, a trivial isomorphism. Again, I'll just point you to this survey paper because I want to stick to C-star algebras here. Any questions at this point? Yes?
Yeah, so these forcing axioms, you mentioned that it is consistent under some cardinal, large cardinals, but so we don't know that it is consistent on the nodes, right? Even there.
It is consistent on the nodes. It's basically, it was, the right way to, if you talk about large cardinal axioms, you just go straight to Martin's maximum, but you don't need that. So this can be done by CCC forcing, and you just have this small fragment of forcing axioms that suffices. So there is no large cardinal strength here involved.
So genuinely it is consistent that these guys don't have inner outer atoms.
Right, exactly. And point here is that basically that means that if you want to construct some non-trivial automorphism, you cannot do it in ZFC. You have to use some extra axiom. And there is one of my favorite theorems ever, so-called sigma 2-1 absolutance by Hugh-Woodin, which essentially tells you that if you're trying something like that, you might as well try continuum hypothesis. There are mathematical reasons why continuum hypothesis is tailor-made to do things like that. There is no mathematical explanation for why forcing axioms do what they do, but it is one of my obsessions, I guess. I would like to see one, but we don't have it at this point. Although everything tells us that there is some sort of analog of Woodin's theorem for forcing axioms, but what it is exactly or what it should be, I don't know. Okay, so next, I would like to say, basically, okay, so let's just recap what has been going on. Under continuum hypothesis, there are outer automorphisms, but all known automorphisms act trivially on Fredholm index, on K1. If you assume forcing axioms, then everything is trivial. So that side is clear. But what remains open is there automorphism, assuming continuum hypothesis, that somehow flips K1. And here's one of the possible approaches. So instead of Cartesian algebra, just look at something that is more convenient to handle. Now, here's the approach. So if you have any C-star algebra which is non-unital, right? So up to this point, all C-star algebras were unital, but now look at non-unital one. One can define the multiple algebra, which is the largest C-star algebra that has your original algebra as essential ideal, meaning its annihilator is trivial. So one has to prove that this actually makes sense. So this is a theorem that this definition makes sense. But this is just a non-commutative analog of Chek-Stone compactification. So here is a little table. If you start with C0, the multiplier algebra is L infinity, and the corona, which is the quotient, is L infinity mod C0. If you start with compacts, then this large algebra is B of H, and corona is Calkin algebra. But there are many other coronas. And these coronas are highly saturated. Basically, there are no separable objects that are actually very important as they're used as a lens to study separable objects. So in many of them, you can define natural X theory, just like the one for Calkin algebra, and study separable algebras by their X semigroups or groups in some cases. Now, so here is a question that is sort of off tangent, but interesting. I think it goes back to 60s. I think Sakai asked it, but doesn't matter. So if you have two separable C-star algebras whose coronas are isomorphic, do algebras have to be isomorphic? Well, the answer is no for some very few reasons. There is easy counterexample. But if you insist that algebras are simple, then it's not obvious. And this is sort of rigidity question that belongs to this. It is not known whether under continual hypothesis you can find counterexample. But Alessandro Vignati proved that if you have forcing axioms, then any isomorphism between coronas of this form has to be trivial. Now, in this case, trivial just means that multiplier algebra, unit ball of multiplier algebra is a Polish space in certain natural topology, and every isomorphism can be lifted by a continuous function between those Polish spaces. And the fact that such continuous function actually acts as automorphism, it is sigma 1, 2, I think. So basically, it's absolute. So essentially, you don't lift it to automorphism, you don't lift it even to homomorphism, but you lift it to something that has to be homomorphism or isomorphism. And from there, one can prove that under forcing axioms, this is basically true. It just leaves some computations. But what I want to talk about is this Brown-Douglas-Fillmore question. So about the K-theory reversing automorphism. So here is a very important C-star algebra called O infinity. Okay, so pick your favorite Hilbert space, which let's say is this one. Then just choose any infinite set of orthogonal projections, so infinite rank. For each one of them, pick a partial isometry between, basically isometry between whole space and space, and generate C-star algebra. Now, no matter how you do, you end up with the same thing. And Joachim Kuntz proved that, so the algebra is called after him. It's O infinity. And it was asked by Dixmier whether this is the case. Actually, I just learned that Dixmier is turning 100 years this year. That's amazing. So operator algebras are good for you. That's the anyway. So O infinity is unit algebra, so we can stabilize it. And look at this corona. Now, if corona has index reversing automorphism, this is a consequence of very deep result by Kirchberg and Phillips. Now, why that matters? Well, if you look at corona of O infinity, or stabilization O infinity, and Calkin algebra, they're completely indistinguishable. They're both purely infinite simple, have exactly the same K-theory, same behavior of X functors, and also same version of Weil von Neumann, etc. theorem. So it wasn't completely crazy to ask, is this corona isomorphic to Calkin algebra? And if the answer is positive, then one could, I mean, the CH, one could just use the K-theory reversing automorphism of corona of stabilization O infinity and just send it back to Calkin algebra.
That other thing called under CH, and this is true in CH.
Yes, yes. So what, right? So of course you wouldn't, you cannot find automorphism which reverses K theory in ZFC, but this is also true under CH. So under CH, this would give you. If you
think maybe under CH they are isomorphic.
Exactly, exactly, yes. Right, so that was actually a question for somebody. Let me. Right, so corona of all infinity tensor the contacts. Right, if you had isomorphism of this and coronal Kalkin algebra, right, you have index reversing here, you just compose, and index has to go to the opposite place. And you know, this has happened before that in our classification program that you have two C-star algebras which are completely undistinguishable by anything reasonable. And yet logicians come and say, well, this is obviously that they are different because there is a first order statement that holds in one but doesn't hold in the other. So one of my points is that logic should be taught more than it is taught. It should be part of you know, general mathematical education. Basically, you know, that's the fact is that first order theory, so just in case that you don't know what I'm talking about, first order theory of any object is just all the statements that you can get by quantifying over elements of the object only. You cannot quantify over automorphisms or over its K theory or whatever, but just quantify over elements. And the fact is that is not a functor. It's not you know, it's not continuous under limits. It doesn't behave in ways that someone who is not a logician would consider nice, but it has some other beautiful properties, and it's really useful to distinguish objects, for example. So what I proved is that these are not isomorphic, and they're even not elemental equivalent. They have different first order theories. I want to say a few words about why is that the case. So it has two bits. Basically, there is certain first order statement that holds in Kalkin algebra but fails inside this other algebra. And the first part, it depends on a beautiful theorem of Simon-Wasserman, who proved that if you look at SL3 of Z, right, so the group of all 3 by 3 integer valued matrices that have determinant equal to 1, that X of the full group algebra of that group is not a group. So what Simon did, he embedded certain C-star algebra C, which is a quotient of that, into Kalkin algebra, and proved that embedding, you know, that embedding is element of X. It doesn't have the inverse. Now remember, by Vokulescu's theorem, identity is star homomorphism which leads to star homomorphism. And there is a very nice description of what star homomorphisms can have inverse. They have to have a lift which is completely positive and contractive. So it's not quite star homomorphism, but something close enough. So what Simon did is constructed something that doesn't have a lift. But what actually, if you just read his proof very carefully, then if you look at, I should define this. So this is all elements A, such that A commutes with everything that is in this algebra. So so-called relative commutant, which is something that you see in operator algebras all the time, that this relative commutant has a property that if you can embed something that is something, C-star algebra, that is simple and unital into this, then that algebra is complex numbers. So no simple unital algebra can be embedded into this. And on the other hand, if you look at the other one, if you pick any separable subalgebra, this relative commutant is going to have a copy of O infinity embedded unitally. Right? So this is a very big difference between them. Now, so this is, this is really not about O infinity. There is a class of so-called strongly self-absorbing C-star algebras, which behave like this.
For your first order sentences.
Sentences, well, you know, you can describe O infinity by it's not so obvious, really. So basically, it is saying that, you know, look, SO3Z is finitely generated. I think it has 2 generators. So it just says there are 3 elements of this, such that whatever commutes with all of them cannot be such and such. Now, of course, there is nothing special. I mean, there is not special, but all that I need here is a property T group, which has infinitely many representations on finite dimensional Hilbert spaces. Once you have that, then the whole machinery works. It's all about property T. Right, so they're all strongly self-absorbing. And more recently, with Gabor-Szabo, no, this is not, the way that I'm stating it is not the way that Gabor would want to see it stated. But there continue many different theories of coronas, which are not only that algebras are simple, but coronas are simple themselves. Simply, we're just using the fact that there are many of these only self-absorbing C-star algebras. I don't want to, this would be a topic for another talk. But I'm going to break one of the rules of colloquial talks. So you know, normally one talks, okay, some people just talk about their results. I tried not to do that. But normally one ends with their result and say, well, this is, you know, the final word. I'm not doing that. So actually, something remarkable happened a couple of weeks ago. So I'll be talking about somebody else's result for the end. Here we are. So remember, the point was indexed reversing automorphism of Calkin algebra. This was detour. Okay, we proved this detour. Nothing interesting there. But now we can say, well, what if we just look at L infinity mod C0 and just say, well, now, what is a Fredholm index -1 operator? Well, it just corresponds to shift on the basis. Right, you're just shifting L infinity by one field to the left, the other joint just moves it in other direction, the first element falls off the cliff. But once you mod out with complex, that's a unitary, and this is automorphism. So is it possible to find automorphism of L infinity mod C0, which has the property that when you conjugate with this unitary, which implements this shift, and then send it to you know, apply automorphism, then what that gives you is conjugation by the reverse shift. Right? So this is just a version. Right? So instead of, let's see, there is no eraser here. Okay. Right, so the original question is, can you have automorphism phi that maps Q of H to itself, such that phi of shift, right, so I define shift there, is the adjoint of the shift. Because this is the unitary with full spectrum and index -1. This one has index +1. So that would be that. Well, that's maybe too much. Let's look at something easier. Remember, L infinity mod C0 is just the diagonal of this. So can you have automorphism like this? Now shift is no longer there, but shift acts on it by conjugation. It is a normalizer. So question is, if you look at phi, maybe I didn't define, okay, sorry, so, but what I mean by AD of S, it is just conjugation, S star. Right, so this is conjugation, and it is automorphism of the algebra. So if you look at phi composed with conjugation by S, can you have it that once you apply phi, you actually get conjugation by S star? This question has been around for at least 10 years. I think it was asked by a few people, myself included, and well, recently, a couple of weeks ago, Will Bryan proved that under CH it exists. No, not by the way, you have to use continuum hypothesis or something like that, because by Sherlock's result, this cannot happen if you have forcing axioms or some funny forcing model. Now, this proof is beautiful. It is completely elementary. So basically, it says that it uses model theory, but model theory is very simple. It's really very intricate and amazingly clever combinatorics. Anyway, so what that means is that at least in this category, you can reverse the index. And, you know, I guess, you know, some of you may be thinking, well, so we are done, right? You just have this automorphism of L infinity mod C0. All that you need to do is extend it to the Calkin algebra, and then shift goes to upjoint, end of the story. However, this is something that we've known for a while. There is another beautiful result of trust. So I want to put it in context. You see, this whole rigidity story, you have certain quotient structures. Continuum hypothesis tells you that they are as malleable as possible. You can do with them whatever doesn't contradict their first order properties. Forcing axioms tell you they are as rigid as possible. Just you cannot do anything that is not obviously doable. Well, that's not quite true. What John Truss observed is the following. If you look at a group of all permutations of natural numbers, and actually throw into it all bijections between cofinite sets of natural numbers. So those are not permutations, but they're almost permutations. When you mod them out by permutations with finite support, you actually get a group. Right? So you have a semigroup whose quotient is a group. All automorphisms of that group are inner. And proof is amazing. So it's, again, super clever combinatorics, just coding somehow conjugacy classes, looking at cycle structures and things like that. But what Truss's result shows for somebody who cares about Calkin algebra is that if you have automorphism of Calkin algebra that sends the diagonal copy of L infinity to itself, then its normalizer is not going to be doing funny things. So basically, normalizer doesn't have outer automorphisms, and therefore this cannot happen. Which means that Bryan's automorphism cannot be extended to Calkin algebra, and really means that his result is not apparently directly relevant in any obvious way. But which doesn't mean that I'm not trying to understand whether it can be done. So that does give us another possible approach here. And well, so I guess I'll just finish 5 minutes earlier. So this is a domestic life photography. Thank you.
Any questions? So what is the expectation? What do you think will happen?
I keep on switching. Oh, this is my reminder, which I obviously don't need. So I keep on switching. So you know, expectation in the sense I wish. Well, I wish that there is one under CH, because you know, if you have that, you know, okay, so far what we have is that Brown-Douglas-Fillmore question has answer which is independent from ZFC. However, the question was really a test question. So whether Calkin algebra has outer automorphisms or not, well, okay, it's interesting that it's independent, but independence of having index reversing automorphism would be something. So that's my wish, but that probably means that the other one is more likely. So basically, I'm trying to prove that there isn't one. And you know, somehow Truss's theorem is closest that one gets to anything like that. But at this point, I don't know. So I don't know.
This result didn't change your opinion somehow? I know you said.
No, of course, I jumped on it immediately and started reading the papers. So it's it's not, it's very specific to, I mean, again, what Will is doing is he's looking at not L infinity mod C0, but power set of natural numbers modulo finite. And it's really about power set of natural numbers modulo finite. But it uses a very clever way of coding homomorphisms. Actually, it doesn't remember X. You have countable Boolean algebra embedding into pure mod finite, and embedding it in such a way that it does the right thing on shift. He has a very clever way of coding those homomorphisms, but certain sequences inside Boolean algebra. And hope is that one can somehow code elements of X by something like that. Now, just to show you the level of our ignorance, take a separable elementary submodel of the Kalkin algebra. Can it have K-theory reversing automorphism? I don't know. But if you have automorphism of Kalkin algebra which reverses index K-theory, then many separable subalgebras are going to be closed under that. So it's necessary at least to have something like that. We don't know, but even if we knew it, which we actually knew in case of Brian's result, it was known that for arbitrarily big countable subalgebras of pure mod finite, you can find something like that, but we didn't know how to extend them. They just define something, you're stuck. And we don't know that either. And even worse than that, if you just look at shift and their adjoint, if you look at monotheoretic type inside Kalkin algebra, the least that one would expect to have any hope is that they have the same type. We don't know. Alessandro actually computed, I think, that up to 2 or 3 quantifiers, they have the same type, but...
Other questions? And let's thank you guys again.